In the last video, we went over the basics of a RAG pipeline, how to design a basic RAG pipeline with basic components. We also went over some of the use cases and why it is useful to use the RAG in a variety of different fields. In this video, I'm going to talk about a little bit more advanced topics on how to improve this RAG pipeline and how to get more accurate answers using your document so that you can create chatbots or text applications that are retrieving information from your data. Okay, so this video is going to be a little bit more technical because we're going to get into the fine details of a RAG pipeline and the different components and how you would work with them so that you can get the best results depending on your use case. There are, like I mentioned in the last video, several use cases, and because they're all different, you wouldn't use the same retriever for all of them. You would maybe create your own custom retriever for your specific use case, or you could use ones that are already out there for the public. And there are new ones that are being created, same with embedding models, they're constantly being updated. And so there's a lot of areas where you can improve your RAG pipeline depending on how you want to interact with your documents. And that's what we're going to be covering in this video. Okay, so to create your RAG pipeline, you first need to create this vector store. You need to collect data, and that can be from API endpoints. If you're collecting data from maybe Facebook pages, for example, you could use the Facebook API or Meta API or Twitter, whatever you're using. You can take information through web crawlers. You can upload your own documents. You could take data from data tables, wherever you get your information. You need to load those documents into your vector store. And the way you do it depends on the type of document that it is. If it's a PDF, you would parse the PDF document differently than HTML from crawling the web, or JSON that you got from an API response. And for that, you have something called document loaders. So you would supply these documents to your document loaders, and that there's different kinds. So I use LangChain. Another popular tool to use is LlamaIndex. The LangChain is a framework you can use to make your RAG pipelines. So LangChain document loaders. You can see that there's text loaders for Markdown documents, or CSV loaders, HTML, JSON, PDF. So depending on what you're using, what type of documents, you have different document loaders. And once you select your document loader, depending on what kind of information you're trying to store, you wouldn't be able to just index one document into the vector store. For example, if one of your documents is a PDF file that has multiple pages, let's just say it has 10 pages, you wouldn't want to map all 10 pages into one vector because it can cover a variety of different topics, and then the semantic meaning can get lost. So you want to reduce your documents to as small as possible so that they capture a semantic meaning, and then the next document covers a different semantic meaning, so that when they get mapped into this vector store and you retrieve them, you're only retrieving the most relevant ones. And for that reason, we have what are called text splitters. And these text splitters allow us to split our documents so that we are reducing the content that's in them, and to make sure that we are only capturing the semantic meaning most accurately, and we can map it accurately to a space. So after you've loaded your document, then it's passed on to a text splitter. And again, there are multiple text splitters. So if we look at within LangChain, you can see over here on the right-hand side, left-hand side, you can split a HTML document by the header. You can split it by different HTML sections, split by different characters. So new lines or double new lines, you can split it that way. These are some very basic ways. I've built a few different RAG pipelines, and for almost all of them, I had to create my own document splitter to capture the semantic meaning most accurately. because these basic ones sometimes don't cut it. But they help you. By understanding these, you can get an idea of how you can create your own custom one. So there's one for Markdown, header splitter, recursive split for JSON. Those are challenging because how do you split a JSON if it's an embedded JSON? You can split it recursively so that you're splitting at the end of a sentence always, or if you're just doing a random split where you're taking a certain number of characters, say 100 characters, you're splitting it every 100 characters. Sometimes you can lose some semantic meaning. You're splitting in the middle of a sentence. So you have to be careful with how you split your documents. And that's why we have all these different options. Semantic chunking, this is one I used and it works okay. I think it's still an experimental. Yeah, it's still an experimental phase. It's not the best, but it can do a pretty good job of splitting a document based on the semantic meaning so that once it's split into, we'll call them splits here. Once the document is split, you have the splits, and a semantic splitter will make it so that each split covers only one semantic meaning, and then the next sentence or the next split at the point where it's split is a different semantic meaning. And that's how this one works. And then you can also do it by the number of tokens so that you have a consistent number of tokens in between each of your splits. And so once you've passed your documents, you've uploaded them, and they've been split, then that's when you get your split documents. I'll just copy this over here. And let's just call these chunks. That's what I always call them. So you get your chunks, and these chunks, these are just snippets of text that are split depending on how what splitter you selected or created. And it's these chunks that are embedded. So they are fed into the embedder model. And once they're fed into that embedder model, you get your embeddings from there. And these embeddings are just vectors. So there's one vector per each split. That vector maps to some semantic space or some vector space that represents its semantic meaning numerically. And then these embeddings are what get stored in the vector store in your index. So this is the flow for taking your documents and indexing them in your vector store. So for example, if I am uploading a biology textbook, for example, there can be a section on, say, photosynthesis, and the section on photosynthesis can be one embedding, and if my question has to do with something other than photosynthesis, then that embedding wouldn't get retrieved because they would be in different parts of that vector space. And just like an LLM, you can also fine-tune the embedding model so that you can get better embeddings of your chunks. And that improves the overall accuracy of your vector store and the semantic space. And these vector stores, they take care of doing the similarity search or whatever technique they use in order to find your relevant embeddings, your relevant documents. They do all the work. So whenever you submit a query to that vector store, it retrieves the embeddings based on that vector, but what's returned to you as a user is the original documents, which is in text. But you also get the vectors, numerical values, if that's what you need, so that you can compare the similarity between the vector that's created from your query after the embedding and the vectors that are associated with the chunks of text. And to improve the retriever, you really want to start with the embedding model. Like I said before, there are multiple embedding models that you can use. The most popular one being Cohere. OpenAI also makes their own that are really good, but Cohere is really popular because the creator of the original embedding model, which is called Esper, is a sentence transformer. The creator's name is Niels Reimers, and he is now working at Cohere. So you can imagine how they would probably have the most accurate embedding models available. And some things that you can control in your retriever when you're configuring it is your top K, so the number of documents that are similar, so like the top 10 results. You can also configure the threshold of the distance that a vector is from your query. So if you have a high threshold, then it will capture more documents in that space. But if you have a low threshold, so a low distance, only the vectors that are very close to that query will be retrieved. And retrieving these documents is all done through the vector store. You wouldn't have to do any of the configuring of how it's being retrieved yourself, because the vector store searches through, it can search through millions of documents in milliseconds, and it's all thanks to the scan algorithm that makes this process very quick. But choosing the right parameters for your retriever, top K results, and your distance threshold, and then also choosing the right embedding model and maybe fine-tuning it really affects your results. Because if you just take a naive approach and you do basic configuration without too much care into how you're getting your documents embedded, then you might have documents that are not relevant to the context and not relevant to the query, or you might not even be retrieving the documents that are in your vector store, but that would be helpful to answer the question. So you have low recall, or the information could be outdated, because that's something that you can do. You can retrieve documents that are the latest information so that you're not retrieving documents that are outdated. Another pitfall for taking a naive approach to creating this RAG pipeline is that your generator, your LLM, could start to hallucinate, and even if you do provide it with right information, it may still decide to use some of the information that it was trained on, because it can't distinguish the factual information from the pre-trained information. The generated answer could be completely irrelevant to the original query, or the LLM might give an answer that could be seen as offensive or not helpful or harmful for your end users. I'm sure we've all seen that scenario in the early days of ChatGPT, where you would ask a question and it would respond with, "I don't know the answer, or I cannot help you with that answer." And you could easily get around those situations if you just prompt the LLM correctly. Okay, so I'm going to quickly cover some of the more advanced components that you can implement in your RAG pipeline. The first one being a RAG translation. So I'll change the color so we can distinguish these from the others. So this would be your text translation. So what you would do with text translation is you could take your input query and translate it in a way that can be helpful. For example, like sometimes your users that are interacting with the RAG pipeline that you've created, or the chatbot that's using a RAG pipeline, they might not know how to ask the best questions. They don't. They might not phrase their question correctly in a way that the LLM can understand, or the RAG pipeline can understand ultimately what they're really trying to ask. One way to translate that query would be to rephrase it. You can rephrase it so that it makes more sense. Or you can rephrase it so that it's better for retrieving. If you know the type of documents that are in your vector store, there's a consistent way to retrieve them, then you can rephrase your query with an LLM so that it makes it easier to retrieve. You can decompose the original query. Say it's a really abstract question, you can decompose it into multiple layers. That way it's broken apart, and you can retrieve the documents based on the decomposed question. You can rephrase that query into multiple different phrases or through multiple different perspectives, so that you can retrieve more documents using that same question, which has similar semantic meaning, but just rephrased differently so that you can retrieve more documents. The next technique that you can implement would be routing. So you can take that original or that translated query, and this is actually called query translation, and you can take that query and run it through a router. So this is the routing step. And then in here, you would provide that query to, say, an LLM, and the LLM can decide what to do with that question. So maybe the user is trying to get data from a SQL database. And so you would provide the query, you could translate it and then provide it to an SQL database as a query rather than providing it to the vector store, because it makes more sense to retrieve the data from an SQL database. Or you can route that question to a different prompt. The prompt is provided to the LLM along with the original query, right? But you could have different prompts. Say you want to answer questions that are technical or questions that are more human. If you want to be more understanding of the customer's difficult situation, then you wouldn't route that query through a prompt that's meant to help them answer a technical question. Another step you can run this through would be a query construction. So in this query construction, you could take the query and reformat it so that it's more suitable for an SQL database. Or you could rephrase it so that it's in the format of a metadata filter. For example, if the user is asking about events that have happened on a specific date, then you can reformat that query so that it creates a filter, a metadata filter, and whenever you're retrieving documents, it's using that metadata filter to only search for documents that happened on that date. The next step that you could implement, or rather improve, would be the indexing. So in the indexing step, you have lots of options for how you index the data. You could, for example, if all of your chunks that you're eventually embedding and then storing in your vector store, if a lot of them have information that's not important, like for example, you can think of an email thread where there's lots of text like, hey, nice to meet you, or it was good to see you the other day, or things like that, where there's not information that's helpful, there's not a lot of detail, then in those scenarios, you could summarize your chunks so that they are, when they get embedded, only the important information gets captured. Or if your chunks are very large pieces of text, I'll go back to the example of the textbook. A whole chapter can be on a specific topic, and you can summarize the entire chunk, which could be very large, into a smaller chunk. So that way, when it's retrieved, you're retrieving based on only the most important information that's in the summary. But then what you actually retrieve is the whole document. So this improves your retrieving because when you create a summary, there's a lot of information. If it's not repeated a lot, it's not repeated often, or it's not the main point, then it might not make sense to try to capture that in a vector, especially for large pieces of text. You might want to narrow them down and summarize them. And so what you would store is a vector of that summary, but eventually it's associated with the original document. And so when the document is retrieved and provided to the generator, you have the full context. And so after you've retrieved those documents, you might find that you retrieved a lot of documents that are not relevant. Depending on what the limit or how you configured your retriever to return X amount of documents, you may have a lot of documents that just don't make sense to provide to the LLM. So what you could do is add a filter so that you could filter out documents that are not relevant. And so in this filter, if you retrieved a lot of documents, say there could be instances where you retrieve the same documents multiple times, you could re-rank all of your documents, and the ones that appear multiple times in your entire list of documents, then those would probably be the most relevant. So a scenario where that might happen would be where you take your original query, you translate it into several different queries, and so you're retrieving multiple documents for each query. Say like you have 3 different translations, you're retrieving documents for each of those translations, and each of them is retrieving like 10 documents. So 3 times 10, you have 30 documents. Some of those might overlap, and then you would re-rank your entire list so that you could reduce your list and you filter out the ones that fall under a threshold, and you eliminate those from the documents that you provide to your LLM. And then if you do find that you filter out too many of those documents, you could loop back into your index and try again, try to retrieve more documents that might have more information. So you could send this feedback into an earlier stage. You could send it to your query translation, so you could retry to rephrase your original query, or you can construct it differently. And then once you do have your filtered documents, you provide those to the generator. And based on the response that you get, you can have an evaluation step where you evaluate the quality of your responses. Evaluation. You run your answer through that. And then if your answer is relevant to the context that you provided, or to the query that you provided it with, it's factual, it's based on these documents, then you have your final answer. But if it's not, then you could have a step where you detect these scenarios and then restart your pipeline, or change some of the steps in your pipeline, so that ultimately you achieve the evaluation results that are suitable for your use case. So that is a more advanced overview of the RAG pipeline and the multiple steps and components that you can implement in your RAG pipeline to improve the accuracy of your answers. And in the next video, we're going to go into the code so that we can see how you can implement these components using Python and LangChain. So if you found this video helpful, please give it a like. That motivates me to create more content like this, and subscribe so that you can see more of the content I produce, and I can help you create and work on your AI projects.